Time to talk about the addition of water to unsaturated compounds. If you treat an alkene with a strong acid, technically hydronium, what you basically have here is your highly polar bond. You have a delta plus on the hydrogen and a delta minus on your oxygen. And so your alkene is ready to attack the delta plus segment of the acidic molecule. And it does it simply by providing its set of pi bonds to create a new bond with that hydrogen. In the process, the hydrogen-oxygen bond is broken and you produce water as a byproduct. But then what you end up getting right here is a carbocation, right? Because the 2 electrons of the pi bond have been utilized to make a new sigma bond. So that leaves the carbon right here with a lack of electrons. It's electron deficient. It's now a carbocation. But the thing to notice is that this is a secondary carbocation. And because it is next to a tertiary CH, that hydride migration can happen to create a better carbocation, a tertiary carbocation. And it is that particular carbocation, the more stable one, that gets attacked by the water molecule that we created in the first step. At that point, you have a protonated alcohol, which, with the use of a base, the base could be the solvent or it could be the conjugate, it could be the anion that was in conjunction with your H3O plus. But the base is going to come in, remove this proton, and the electrons will go back to the oxygen to form your final alcohol. Now, the big point of this sequence of events is that rearrangements can actually happen when you're doing addition reactions with strong acids. And that can be a little bit inconvenient from the point of view of synthesis, because you might be trying to actually get that alcohol in this secondary position and you don't want it to end up on the tertiary position. That could very well be the case, and the rearrangement is going to make matters a lot more difficult for you. Now, a reaction that is somewhat related to the hydration of alkenes is that in which there happens to be not only water present but also a dihalogen like dichlorine. Now in this case, the chlorine-chlorine bond is the weakest bond in the entire set of reactants right here, and by default, chlorine is the better, more polarizable atom. That's the one the alkene is going to attack. So we have the pi bonds being supplied to one of the chlorines. The set of electrons that used to be part of that bond are now kicked out to the second chlorine to form chloride, and you form once again that secondary carbocation that can rearrange to form a tertiary carbocation. And right here between chloride and water, water is probably going to be used not as an equimolar reagent but rather as a solvent. So you're going to have a lot more water than you do have chloride, and because of that, the probability of the water attacking the carbocation is a lot higher than chloride. And so the likely product is going to be this protonated alcohol, which once again has a base, like in this case the chloride could come and remove the proton, forming HCl in the process, to now give you the product. And the thing to notice right here is that this is almost identical to what we did with the H3O plus, except that instead of adding H plus, we were adding the chlorine atom. So now we have this product that contains a halogen and an alcohol in the same molecule, and together this product is known as the halohydrin product. Halo because of the halogen, and hydrin because of the presence of OH, making your alcohol. So this is very common of doing reactions that have the two solvents, water and then the organic material, to which you add chlorine gas. It could even be bromine gas, or excuse me, bromine liquid, to make this happen, right? So that's something to be aware of. And sometimes this is actually a pretty good product to make because the chloride here is a decent leaving group, and we can use that to form some exotic epoxide-like rings, or perhaps some other rings that contain the oxo atom within the cyclic structure. All right, but as stated, just trying to add water directly, or H3O plus, to the alkene leads to this rearrangement business, which is rather inconvenient. If instead we use a few other reagents, we can circumvent this problem. And the first one is mercury reagent, mercuric acetate. And what mercuric acetate does is it technically interacts with that alkene. And before I can tell you how, I want to point out that the bond length, so if you look at the bond length of the carbon-carbon double bond, that bond length is about 1.34 angstroms. And alkynes, the carbon-carbon triple bond, is about 1.20 angstroms. When you look at the atomic radius of the elements, in particular the atomic radius of mercury, the radius of mercury is 1.16. And what that means is that if we treat mercury as a sphere, then technically speaking, the entire width of that mercury atom is going to be about 2.32 angstroms from left to right in that hypothetical sphere, and that is way bigger than the size of these bonds. So you could definitely have the mercury in essence sitting on both of these carbon atoms, or both of those carbon atoms, when it does interact with them. And this is the premise for the reactivity that we're about to mention. So the first thing that takes place is that one of the acetates comes off, and the alkene attacks the mercury. So it actually forms a carbon-mercury bond. All right, so you have your acetate leaving group in that process, and this creates technically a carbocation. So this will be a secondary carbocation. But here's the kicker: because mercury is so big, you don't actually form this carbocation, because mercury, as a result of its size, is basically technically sitting on top of both of these carbons. So it does create a pseudo metallocyclopropane structure, in which basically the mercury is preventing attacks on this carbon that would have been the secondary carbon forming. This is known as the mercurium ion, and the mercurium ion basically makes it impossible for the hydride, to migrate over to here and lead to a rearrangement. And so what now happens is that the water, instead of attacking what would have been the tertiary carbocation, it attacks the direct carbon where the double bond used to be, right? So the mercury attaches to this carbon on the right side, the attack happens on the carbon on the left. And one way to also look at this is that because mercury is so big, mercury prefers to stay on the carbon that has the least amount of steric bulk, the least amount of substitution. So notice that here we've drawn the lines segmented, kind of emphasizing that mercury, it is stabilizing that carbon, but technically speaking, it's only partially bonding to it, whereas the real bond is to the carbon that is the least substituted out of the two. So when the water comes in, it will do so by attacking the carbon that is the most substituted, or the carbon that has the most steric bulk around it. And the mercury will end up on the opposite end. Alright, so two things to be said here. Because of mercury being so big, rearrangements don't happen. And two, because mercury is sitting on top of these two carbons, there is no room for the water to attack from the top portion of the molecule. It will have to attack from the bottom portion. And vice versa. Mercury could be sitting on the bottom side of the molecule, in which case water could only attack from the top. The end result is that the oxygen atom is going to end up bound in an anti-configuration in respect to the mercury, because it has to attack from the opposite face of the molecule. Alright, now, generally speaking, having carbon-mercury bonds is not a good thing. they tend to actually be quite toxic compounds, and so we will want to get rid of the mercury and just end up with a regular organic molecule instead. So here's where we utilize and make use of electrochemistry. Because if you look at the electron potential diagram right here, with the species that are the most oxidized on the top portion of the diagram and the most reduced versions of the element on the bottom portion of the diagram, what we do see is that hydride, which is all the way down to an electron potential of negative 2.25, that's a very reducing component. And when you compare it to Mercury 2, Mercury 2 is all the way up here. And when you're looking at these diagrams, the idea is that if the two regions of the species in question, technically your reactants, don't overlap, then it is guaranteed that if these two components come in contact with each other, they are going to react with each other via an electrochemical reaction, in such a way that you end up producing products that will overlap with each other. In particular, mercury 2 will be reduced all the way to neutral mercury, and then your hydride can be oxidized to H2. And notice that here H2 and mercury definitely overlap with each other in terms of the electron potential diagram. So those are your products of mixing hydride with mercury, right? And then mercury, which is a very dense liquid, can be easily separated from your organic material, because the organic material will be sitting on top of the mercury. So you could just literally pipette away the organic solvent with your organic product and leave the mercury behind. So one way to make this happen is to use a relatively benign reagent, sodium borohydride. This is a BH3, which does contain a hydride within it, and so it delivers only one equivalent of H minus to this molecule. And because of the electrochemical reaction, the mercury gets reduced to mercury 0, and the hydride gets oxidized not to H2, but rather it gets oxidized to the carbon-hydrogen bond that you see right here. In the process, you of course kick out sodium acetate and you form BH3, which is the component now without the hydride, right? So one common mistake that sometimes people make is they'll see that there's 4 hydrogens there, and they'll assume that all 4 of those hydrogens behave as hydrides. And the actual truth of it all is that only one of them is hydridic. The other 3 are very much bound to the boron via covalent bond, a true covalent bond. But the 4th hydride, since boron only has 3 valence electrons, the 4th hydride has to come in with the 2 electrons from the get-go. And the boron does not provide any electrons to that 4th hydrogen. So that last hydrogen definitely is hydridic, and it has a potential for reducing things. So that's how you go about reducing the product. And one way to kind of think of it is that when you combine these molecules, you could envision the acetate being replaced by the hydride via salt metastasis reaction. And then from here, you just have the hydride migrating to the carbon, the electrons of that carbon-mercury bond going back to the mercury to give you your reduced mercury and your newly formed alcohol. Now, this is an oversimplification because the actual true mechanism involves radical intermediates. And so we're kind of avoiding all that because, we just don't want to make it overly complicated. But the key idea is that by introducing sodium borohydride, you will remove mercury. And not only that, but the hydrogen that's replacing the mercury is going to end up exactly in the same position as where the mercury was. And what that means is that your new hydrogen is going to be in the anti-configuration in respect to your oxygen. So those are the things to keep in mind. No rearrangements, you end up with the anti-configuration. And technically, this is your Markovnikov product because the hydrogen ends up on the carbon that has the most hydrogens to begin with. All right, now let's take a look at the alkynes in respect to mercuric acetate. A similar idea takes place here, and here you will form the alcohol, technically an alkene alcohol known as an enol, and the idea is the same as with the alkenes. The mercury sticks with the carbon that is the least substituted, so that will be the carbon right here on the right side. The OH that comes from the water will be bound to the carbon that is the most substituted, or the one that has the most steric bulk, so the one here on the left. And that's what we are observing. The oxygen is on the left carbon. The carbon on the right is going to ultimately be substituted by the hydride, and these two are in the anti-configuration. All right, but there is one more thing to be said. When this reaction is happening, the borohydride is technically a basic substance, so you have slightly basic conditions right here. And what happens is that this particular enol that you're forming gets attacked by the hydroxide that's present in your aqueous solution, and the electrons of that OH bond are moved over to form a new oxygen-carbon double bond. But at the same time, this carbon-carbon double bond has to get out of the way and form a carboanion. And then that carboanion, being basic enough, can attack the water that you just formed in the first step, thus reforming your hydroxide, right? So you don't need a lot of hydroxide because technically it's catalytic. And the end result is that you don't actually stop at the enol, but rather you form this new ketone. And ultimately, the reason this does happen is because the energies from the bond association arguments, the bond association enthalpy arguments, are a lot more stable when you have a carbon-oxygen double bond molecule and a carbon-carbon single bond versus having a carbon-carbon double bond and only a carbon-oxygen single bond. So this is all driven by thermodynamics, pretty much. But this is something to be aware of. This is known as tautomerization. And you will see this a lot in the next semester class of organic chemistry. Yeah, this is kind of like a little taste to it, but you have to understand that this is what's happening to predict that your product is not the enol, but rather the ketone, right? So this is the actual product, this thing down here. Okay, in the next video, we're going to talk about hydroboration, and this will be another means by which we can introduce water without rearrangements, but that will allow us to do so in an anti-Markovnikov manner. Okay, so see you in the next video.